Hi, I'm John Urschel, and this is MIT course 18.191, I believe, Computational Thinking. Alan Edelman was nice enough to bring me in for one little mini lesson, and so what I'd like to do with you all is to pick up where Alan left off last lecture, talking about Poisson's equation and the concept of trying to approximately solve some differential equation using some sort of discretization and solving some system of equations. So I really want to dig into this concept and really take a higher level view of this. And hopefully along the way, we can learn some lessons about just how to think computationally when it comes to approximately solving continuous problems. So to start, what I'd like to do is I'm going to pull up my iPad and I'm going to share screen. Bear with me. I have a nice setup. I've got my my iPad here, my MacBook here. I'm a walking advertisement for Apple, so I've got that going for me. Just one little snapshot from Alan's lecture last time, and if you haven't noticed by now, I am strongly encouraging you to go watch Alan's lecture. Hopefully there'll be a link somewhere pointing you to it. And what he talked about last time was Poisson's equation, namely setting the Laplacian of some function, here he calls it f, equal to another function g on some domain, and fixing our function f on the boundary. And what he talked about was trying to approximately solve this problem by taking our domain and trying to discretize it by creating a grid, which he illustrated down here in the bottom. And by trying to solve a system of equations on this grid, you can obtain approximate solutions to Poisson's equation, the continuous problem. And so what I want to do today is I really want to get hands-on with this concept, try to set up some differential equation, which has some sort of semi-realistic real-world setup, set up our system of equations, use an iterative technique to try to approximately solve this, something like Jacobi method, which Alan already introduced to you all, and try to understand something about the right way and the wrong way to try to solve a problem like this, okay? So to get started, let me just say that I will be using slightly different notation than Alan did in his previous lecture. So the problem we want to solve is not quite Poisson's equation, because our setup is going to be the following. So the idea for our problem is we want to solve the equation second derivative of some function u, which depends on x and y, with respect to x, plus the second derivative for u with respect to y. Well, we want this to be 0 on some domain, which I'll just denote by omega. And then we're going to want our function u to be fixed on the boundary. Okay, and just to give you something to imagine in your heads, the continuous sort of semi-made up problem that I want us to think about is, let's suppose we are looking at some room, and let's say we're looking at a bird's eye view of a room. Let's say it's a square room. This is a square. Let's just go with that. And let's suppose this room, it has walls which are decently well insulated. It has a window right here, let's say. Here we have a window. And so you can imagine this space is the outside. And let's say it's cold outside. The temperature at the window is 5 degrees Celsius. Here, this wall and all the other walls touch other walls in the building. So let's say the temperature here on this wall, 21 degrees Celsius. Maybe at this corner, it's 13 degrees Celsius, 13 degrees here. And the way in which the room is heated is, let's say there are two heaters in this room, one right here and one right here. And both of these stay at a fixed temperature of 40 degrees. And let's suppose that in between all these temperatures, the temperature changes at some constant rate along the walls. Okay. Now, suppose we wanted to figure out what the temperature is at any given point in the interior of this room in the steady state. Like suppose these temperatures are fixed on the boundary, the heaters are fixed at 40 degrees, and we want to know eventually, what does the temperature look like inside this room? Well, what we can do is we can try to solve this equation, which this equation up here is Laplace's equation, which is a specific example of Poisson's equation when the right-hand side is equal to 0. By trying to solve Laplace's equation, where our domain is just the inside of this room, and U on the boundary is just the temperature at any given point on the walls or at the heater, we can try to solve this differential equation to come to understand what the temperature inside the room is like. And so this differential equation is actually slightly harder to solve by hand than most because of these heaters. These heaters are popping out. If these heaters weren't popping out and they were just on the sides, you could actually somewhat solve this by hand by using the sort of method of superposition plus using like a Fourier series for each side. If that means something to you, great. If it doesn't, don't worry about it. The point is, the fact that these heaters are here actually means that, we might actually need to use computational techniques to find the solution. So if we want to use computational techniques to find the solution, what we should do is we should overlay a grid on our domain. And this is by pure coincidence, but the paper the virtual paper I'm writing on my iPad actually has lines. And so you can imagine that we actually set up grid points where we have points here like this and just connect it like so. And again, from Alan's lecture last time, you know that the discretization of the equation, let's say second derivative of u with respect to x plus second derivative of u with respect to y equals 0, let's say, the discretization of that at some grid point, let's say we're at grid point ij. So this is ij. We can approximate that equation by instead trying to ask that the following condition be satisfied. We can ask that u of I plus 1 j plus u I times j plus 1 plus u of, let's see, what else did I do? I minus 1 times j, and finally plus u I j minus 1, all minus 4uij. We can set this equal to 0. And this, how you get between this equation for derivatives and this equation for the value of u at these discrete points, this just follows from approximating each of these second derivatives by a sort of a discrete approximation that comes from using Taylor's theorem. And Alan touched on this during his last lecture, so I will leave it at that. If you sort of want to understand how we get this equation from this continuous problem, I encourage you to look at the last lecture. And so to solve this, this sort of heater problem that we have, what we can try to do is we can just solve the following equation for I and j in our grid. And to do this, of course, we're going to have to code something. We're going to have to compute something. And this is where we get into the actual sort of practitioner. And this is where we get into the actual use of coding to solve this problem. So now I'm going to shift from my iPad. What you see here is a Pluto notebook where I coded up a little something in Julia. And so let's go through this and I can talk you through what I've done, and we can look at how we can try to solve this system of equations. And what we're going to do is we're going to look at some naive ways we could try to solve this system of equations, and some cleverer ways to solve this system of equations. So let's get started. First, what we need to do is we need to define our grid. So I wrote this function, grid with boundary, which takes in some integer k, which tells me how many boxes I want in each direction, in the x and y direction. It's 2 to some power k. So if I set k to be 5, that means I get 32 rows of boxes and 32 columns of boxes. And now what I've also done is I've added these boundary conditions that correspond to the sides of the room. So here what we see is this 5 corresponds to the window being 5 degrees Celsius. The 21 corresponds to the wall, which is sort of away from the window, being 21 degrees Celsius. And you'll notice sort of one nice thing about Julia is that I don't even have to write any type of, I don't have to write this right-hand side here as 5 times some array, which is an array of ones, which is the same size as what I'm mapping it to. I can just write 5, which is quite nice. And so I've defined my boundary conditions. So I've set up my grid, I've set up my boundary conditions, which, if you're curious, looks something like this. So up here in the top right, this is where the window is. These are our 2 heaters. And down here is the wall, which is opposite the window, which is at 21 degrees. Okay, and you can see the heaters are at 40 degrees. Yes. Okay. And so what we want to do is we're just going to run Jacobi a bunch of times and try to get an approximate solution on our grid. So the first thing we need to do is we need to code a function which does the Jacobi update. So here I have a function, Jacobi step, which takes in some matrix T, an abstract matrix. We can think of this as an array. It takes these values m and n, which tell us how many rows and how many columns does our array have. And what it does is it just picks every single point in the interior of our array. So we're ignoring the sort of the 2 boundary columns in the sort of first and bottom row. And for each of these points, we're defining this new array T prime to simply equal the average of T of its neighbors for Tij. And so this is just the Jacobi update, which I showed you and which Alan has already talked about, but now it's coded for you. And now to get an approximate solution, we just define this function simulation, which takes in an array, some tolerance for error, and some number of steps that you may want to run. And all it's going to do is for that number of steps which you define, it is just going to run Jacobi over and over again until either you do all the iterations you tell it to do, or its error drops below a certain threshold. And I've defined this function add heaters here, which you don't need to worry too much about. But this is simply to make sure that the heaters stay at 40 degrees and allows us to write a more generic Jacobi function. So that's the point here. And we see if the maximum sort of error between our old approximate solution and our new approximate solution is less than some tolerance epsilon, then we're just done. Okay. And so you can see that when we define an array T, grid with boundary, this sets up the boundary conditions. What we get is some array. Here it's 33 by 33, which corresponds to having 32 rows of boxes and 32 columns of boxes. And what we're going to do is here we perform a simulation where we do up to 5,000 iterations of Jacobi, and we want an error that's right around 10 to the negative 10. And so here what I've done is this really cool operation, which is great for visualizing things. I've actually stored all of the iterates over the simulation in this cell results. And so what I can do is I can draw a heat map of any sort of one example of these results. And I can actually bind this variable I to the slider I have here, which will now go over the different iterations. So here in this image, you see this is our starting situation. And as I do iterates of Jacobi, oh, that moved quickly. Let me try to do it slower. So I move iterates of Jacobi, you can see how our approximate solution changes over time. You can see it's slowly filling in. It takes a little bit of time. This is due to the fact that Jacobi is inherently a local algorithm. You see it only changes a grid point based off its neighbor. So it can take some time for some changes in one part of the grid to get to another, which is one of the big downfalls of Jacobi. But as you'll see later, we'll come up with a way to fix this. And so here, what we have is on our course grid, which is a 32 by 32 grid. We have an approximate solution. We've solved this system of equations on our 32 by 32 grid almost exactly. And now we're starting to get a sense of roughly what our continuous problem, roughly what the solution for our continuous problem should look like. Although we realize that we have a very coarse grid, and so there's error between this exact solution on the coarse grid and the continuous solution. And you can even sort of see the squares when you look at it. And so maybe we want something more accurate, which means we're going to want a solution on a finer grid. And so let's try to solve this problem now, not on this sort of, what is a very sort of grainy and coarse 32 box by 32 box grid. Let's try to solve this on a finer grid so that we can really get a good approximation to the continuous solution. We already know that our function u should roughly look like this picture, but now we just want the picture to be a little bit clearer. We want to sort of just decrease the error a little bit. So the first thing I should note is that we need a better initial condition because Jacobi, like I mentioned, is a very local method, and somehow putting zeros everywhere in the interior to start is a terrible initial condition. What's a good initial condition, you might ask? Well, one good initial condition is to do the following thing. Take any grid point in your interior, and maybe your first guess for this grid point could be a weighted average of the temperature at the 4 walls that are sort of like, if you go straight from that point, you go straight up, you go straight down, you go straight to the left, and you go straight to the right. And maybe we average the 4 temperatures at those walls based off how close or far away our grid point is from the wall. If our grid point is close to the wall, it should get a very high weight. And if it's far from the wall, it should get a low weight. And so in this function initial condition, I simply come up with a weighted average of the boundaries to define the grid points. The This is an example of linear interpolation. If this is a word you know, if you don't, then this is no big deal. And so now I'm defining this TT prime to be my new initial condition, where now I'm not on a 32 by 32 sort of square grid, but now I'm on a 1024 by 1024 square grid. So now I really have a fine grid and I really have resolution here. You look at this picture here, the heat map of my initial condition, and you can see that it really looks like a picture. It doesn't look grainy. You can tell that we have a fine enough grid that we're really somehow getting something which should start to look very much like the exact continuous solution. Let's say if we try to solve the system of equations on this 1024 by 1024 grid. And this is what we're going to try to do. So the first thing we're going to try to do, which is the natural thing you might try, is, well, we're just going to try to run some number of Jacobi iterations, and hopefully we'll get to the exact solution on our fine grid relatively quickly. And so what I've done here is I've run our simulation. I want just an error of 0.001, and I'm giving it 500 iterations. And so here I'm using the same binding as I did before. This is a really cool sort of thing you can do in Julia. And so here I'm slowly but surely doing Jacobi iterations. Here's 20 iterations. It's going to take a second to show, but okay, I did 20 iterations. Kind of looks the same. Let's do 50 iterations. Kind of looks the same. I did 100 iterations. Pretty much looks the same. And now let's just go all the way out and let's look at, let's say, 400 iterations. You can see there are some differences. Like you can tell that around the edges and around the heaters, things have smoothed out some. But very much the picture after 400 iterations of Jacobi method and the original initial condition, these two things pretty much look the same. And you can tell that after doing 400 iterations, which on a very fine grid, this can be expensive, we really have we've gotten no closer to the exact solution, which you should think should probably look like a sort of, should probably look kind of like this picture here, which we had from our course grid, only with a little bit more smoothness. And so because we know that this is the exact solution on our course grid, and that this course grid approximates our continuous solution, albeit not as well as an exact solution on the fine grid would, we know this is roughly what the exact solution on any fine grid should look like. But the problem is that after 400 iterations of Jacobi on our 1000 by 1000 grid, we're really a long ways away from there. And I've got news for you. It's going to be a long time before this picture starts to look like what it should. Far more time than we have. I can tell you that doing these 400 iterations, this already took 20 seconds. And I can tell you that to get to the type of picture that we want, it's going to take a very, very long time. Now the question is this unavoidable? Is there nothing we can do to try to speed up this computation and to try to get a good solution on this fine grid? Well, you can start to think about it for a minute. What could we make use of? What do we have? Well, for one thing, we already roughly know what we think our solution should look like because we have an exact solution for a coarse grid. And we know that the exact solution on a fine grid should look very much similar to the exact solution on the coarse grid. Why? Because no matter what resolution you choose, no matter what sort of, no matter how many rows and columns you choose, we know that all of these grids are approximations to our continuous problem. The finer the grid, the better the approximation, but they're all approximations. And so rather than starting with some initial condition, which is not so bad, this initial condition, and using Jacobi, why don't we try to use the exact solution on a coarse grid as an initial guess for a fine grid to try to speed up our computation? Okay, let's try to think hierarchically. Let's try to think in a multi-level way. Okay, so what we're going to do is let's just look and try to approximately solve a problem on a coarse grid. So here, what I'm defining here is very, very coarse. This is a 16 by 16 sort of square grid. There's 16 squares in, there's 16, there's rows of 16 squares and columns of 16 squares. So this is very coarse. We have our initial condition. We run Jacobi. Here, we run about 900 iterations of Jacobi to get the exact solution, which you see right here. And again, we see that this, yes, it looks sort of grainy, it looks sort of out of focus, but we know roughly this is what the solution should look like, just with better resolution. And the thing to keep in mind is that even though this took us 900 iterations of Jacobi to get this exact solution on our coarse grid with pretty much no error, the thing to keep in mind is that we would have to do 4,096 iterations on this coarse grid for the computational cost, the sort of number of operations our computer does for this coarse grid to equal one iteration of Jacobi method on the fine grid. I want you to really, really keep this in mind because this is an important thing to sort of remember. The fine grid has 2 to the 10 sort of square rows and 2 to the 10 square columns, but our coarse grid only has 2 to the 4 by 2 to the 4. And so the thing is, our fine grid has roughly on the order of 4,000 times as many points as our coarse grid. And so that means roughly one iteration of Jacobi on our fine grid is 4,000 times as costly or expensive as one iteration of Jacobi on our coarse grid. So that means this picture for our coarse grid, which I got, costs less than one iteration of Jacobi on our fine grid. And so we can try to really exploit this. There's a natural algorithm which is coming out, which is to solve our problem on a coarse grid and then use the coarse grid as an approximation, as an initial guess for a finer grid, run Jacobi some more, and then repeat and just start from a very coarse grid, like a 16 by 16 grid, and just slowly but surely move our coarse grid to one that's slightly finer. So maybe we go from 16 by 16, we solve this. Then we map it to a grid that's 32 by 32. We use Jacobi, we approximately solve this. Then we map that solution to a grid that's 64 by 64, and we approximately solve this. And we keep going until we get to our grid, which is 1,024 by 1,024. And what we'll see is that it's going to cost much less. And so the first thing which I want to define is this function up level, which takes an approximate solution on some grid size, let's say 16 by 16. And what it does is it maps it to a grid which is just finer by a factor of 2 in the number of rows and a factor of 2 in the number of columns. So if this takes in a matrix, an array T, which is, let's say, sort of 16 by 16 rows by 16 columns, it's going to output something which is defined on a grid with 32 rows and 32 columns. And one natural way to do this, which I have commented out, is to simply define the value at some grid point for the fine grid to just be the value at the corresponding coarse grid point when you divide by 2 and you truncate. So this is one natural choice. I chose something a little more complicated to for every fine point I'm going to take the average of 4 course points, which are nearby it, using floors and ceilings. But even using this simple sort of concept, you can see we get a natural approximation on the fine grid. So if this was our exact solution on the coarse grid, by mapping this up to a grid which is just 2 times as fine in the row and 2 times as fine in the column, you'll see that that same picture is now on a 32 by 32 grid. And now that we have this better initial guess, we just use Jacobi, and we're going to get a better solution. And so we can code this in the following way. This function multi-level takes in an array T, an initial guess, and it tells us, and it takes in some K final, which is the resolution of the final grid we want. So for us, that's going to be 10 because we want 2 to the 10 rows, 2 to the 10 columns. And all this does is from our coarsest grid to our finest grid, we're just going to do simulations of Jacobi. And then we're just going to take our approximate solution and we're going to map it up to 1 grid finer. And we're just going to keep doing this until we get to our finest grid. And so by doing this, here you can see that this runs, this whole procedure, this multi-level procedure of doing Jacobi over and over again, runs in about 1/4 of a second, as opposed to the approximately 20 seconds the other iteration did. And you'll see that the number of iterations, okay, on the 16 by 16 grid, it did 112 iterations. But then when it maps it up on the 32 by 32 grid, it only needed 20. On the 64 by 64 grid, it only needed 15. On the 128 by 128, it only needed 11. And you can see that it's decreasing as you're moving our approximate solution to a finer and finer grid. And one thing to note is that iterations on coarser grids are cheaper because there's less points. And so what you can do is if you weight each of the iterations, the number of iterations at each level, based off the factor of how many fewer grid points it has, the thing you'll note is that at the end, the cost is very, very small. So here, this whole multi-level procedure, which I just coded and I have run, the number of sort of iterations that this would cost on the finest grid is the equivalent of less than 7 iterations. Okay, so before, if you recall, we did about 400 iterations and we saw almost no change in our initial guess. And this is because Jacobi is a local algorithm, and this, it really takes time to see global changes. Well, by being intelligent people, by making use of the fact that we're not just trying to solve this 1024 by 1024 system of equations in some black box. We're not just, given this problem and this is the only problem there is. Because what we're fundamentally concerned with is this continuous solution, and we get to choose the grid we want to use or which grid we want to use when, we can make use of this knowledge to do something more intelligent. And by using this more intelligent multi-level procedure, you'll see that we did 6.3, the equivalent of 6.3 iterates of Jacobi, but yet you can see that our solution very much looks like almost the exact solution. You can see that this is truly a finer grid version, a very smooth version of what was the exact solution on a very coarse grid. And that just took the equivalent of less than 7 iterations, as opposed to 400 iterations here, which does almost nothing to our fine grid. And so 400 iterations for something that doesn't really tell us anything about the right continuous solution versus the equivalent of 7 iterations, which gives us what is almost the exact solution with a very high resolution. This is the power of thinking hierarchically. of, given some continuous problem, not just sort of getting down in the weeds and sort of saying we're going to discretize to some grid and forget that you have a continuous problem to rely on, but to remember that you choose your discretization and you choose when you want what level of discretization. This is just one specific example of a multi-level technique. This is something people might call a Cascadic multigrid method, which is a specific example of a family of multi-level techniques for solving differential equations just like this, called multigrid methods. There are more sophisticated versions which ask the very simple question, well, once you get an initial guess and you get it all the way to your fine grid, if you want a better solution, if you want to decrease error even more, you don't have to stay on your fine grid and keep using Jacobi. You can actually take your approximate solution and you can look at the error for your approximate solution and map that back down to a coarse grid to further speed up your computation. And procedures like this are called V cycles. There are things called W cycles, which I encourage you to look up on Wikipedia, which are more sophisticated versions of what I've shown you today. The main thing I want you to take away from this lecture is that whenever you're trying to solve some sort of problem, it's important to remember that it's important to fundamentally remember that it's the problem you want to solve, not the discretization, and that your choice of discretization, your choice of solver, these are all arbitrary techniques that you choose. And it's important for us as computational people, as computational thinkers, to make sure that we're being intelligent and making sure that we are sort of doing efficient computation, that we're not computing more than we have to, and we're not making mistakes because we don't understand the bigger picture.